So welcome to the lecture again on aerodynamic basics, right? So today we will discuss about the basic integrals, that is line integral, surface integral, volume integral, and the relation between them. And also we will discuss the various fluid models, right? So I acknowledge John D. Anderson's Fundamentals of Aerodynamics, right? So let us consider the vector field, right? We know that A of x, y, z and A of r theta z and r theta pi are the different coordinate system. So this is Cartesian coordinate system, and this is cylindrical coordinate system, and this is spherical coordinate system, right? So let us consider a curve C. This is the curve C from A to B, right? This is A and this is B, right? Let ds be the elemental length. Here you have a ds, that is elemental length, right? And n be the unit vector, which is tangent to the curve, right? Now, we want to define the vector ds that yesterday we have seen n is equal to ds by modulus of ds, and we can define in this notation. Now the line integral A, right? The line integral A along the curve C from point A to B can be represented by the integral A to B A dot ds. Now, this curve is an open curve, and if you have a closed curve, so, right, let us assume the closed curve C, then the line integral can be written as a closed integral over C A into ds, right? So, this is information on line integral. Then let us talk about the surface integral. So, this is an open surface. Yes, right, and it is bounded by a closed curve C. So this is a closed curve anyway, right? And you know, any fluid element, if you consider at a time t, and if you consider there is a flow of fluid, and at a time t plus del t, there is change in time, the fluid shape may change, right? So we will discuss all those things, but before that we need to understand what it is, right? So at point P on the surface, let ds be the elemental area. So this ds is the elemental area, and there we have mentioned the d and the small s, right? So the surface integral can be written in all these forms, say the double integral over the surface S P into ds, right? And here the P is a scalar, right? And the result is a vector. Here again double integral A ds, and A is a vector. You know, AXI plus AYJ plus AZK, right? And the result is scalar here. And again A cross ds, double integral over S, A cross ds, that is the surface integral of a vector A over the open surface S, right? Here the resultant is a vector. Now, in the surface integral, say we can, if the surface is closed to surface, right? If the surface is closed to surface, it means that there is a volume V, okay? And this surface is a closed surface. Assume that, usually I say that you know the bean bag in the home, right? You can assume the bean bag in the home, and we can consider the ds as a surface, right? Elemental surface, right? And the surface integral can be defined as double integral, the closed double integral P into ds and A dot ds and A cross ds. So the surface integral can be represented in this way, right? Next comes the volume integral, right? So let us consider V is the volume. You know the volume here, right? Here is the volume V, and the rho be any scalar, right? Any scalar field where we can consider density or so. Scalar field in the space, then the volume integral over, the volume integral over the volume V of the quantity rho can be defined as the triple integral, the closed integral over volume rho into d, right? Again, let us consider A be a vector, right? A be a vector and A be a vector field. Then we can write the volume integral as triple integral volume A into d, right? So this is the representation of line integral, surface integral, and volume integral. Now, let us think about the relation between the line surface and the volume integral. And you might have studied this Stokes theorem, divergence theorem and all, right? But anyway, we will revisit. Let us consider an open area S bounded by the closed curve C, right? And let A be the vector field, and the line integral of A over C can be related by Stokes theorem. So the closed integral over C A dot ds can be expressed as the surface integral del cross A into ds, right? So this is what called the Stokes theorem, right? Now, divergence theorem, right? Divergence theorem relates the volume and the closed surface. So we can express this as double integral over S A dot ds is equal to the triple integral over V del dot A into d, right? So then we go to the gradient theorem, right? So in the gradient theorem, if P represents a scalar field, a vector relationship analogous to the divergence theorem, which we have done here, right? We can, this is a vector relationship, right? Now here we can write double integral P ds can be equated to the triple integral over V del P dv. So this is our discussion, right? Where initially we have started with line integral, surface integral, and volume integral. Then the relationship starts with the Stokes theorem, divergence theorem, and the gradient theorem. Right? Because we will be using this in deriving a lot of things in future, probably starting from the continuity equation, momentum equation, energy equation, and so on. And hence, I want you to look into that. Now, we know in aerodynamics, we have a lot of things which we need to imagine, right? So aerodynamics is basically a fundamental science with the physical observation. So if you say most of the aerodynamists all over the world, they may be thinking, in a similar way. For example, the physical aspect or physical intuition. For example, if you ask an aerodynamist, if you give him an aerofoil and if you give him a circular cylinder, right? You know the aerofoil, right? The aerofoil and say a circular cylinder. And if you ask the aerodynamist their intuition on the drag and the lift characteristics, as well as the skin friction drag, pressure drag, whatever it is, they talk from their intuition, right? And also, they can make a reasonable judgment on various problems based on their intuition. That is because of the basic understanding in the fluid mechanics or aerodynamics, right? So it is necessary for us to describe a fluid motion, describe a fluid model, right? So there is a philosophical procedure for that, and we will discuss about the procedure now. Before going to the procedure, let us describe the fluid motion, right? So here is the description on Lagrangian and Eulerian. So Lagrangian is traveling in a boat, right? And Euler is standing on the bridge. So it means that the Lagrangian, we always discuss about the parameters rho, v, pressure P, whatever it is, at a point. So this point, it will be keep on moving and it is keep on changing. But Eulerian approach, right? Eulerian approach is entirely different, because Eulerian approach considers at a particular point, right? At a particular point where it doesn't move, it observes the fluid which is moving at that particular point. So say single fluid particle, that means you are traveling along with the fluid. You are traveling along with the fluid and observe the properties of the fluid, then it is Lagrangian. If not, you are staying in a particular point and observe, then it is a Eulerian approach. So with this two approach, we may have a lot of other discussions in the next sections, right? So we start the expression for the fluid models, right? So there is a certain philosophical procedure, as I told. So that is involved in the development of the equation in fluid dynamics, right? So we will start with that. This is the number one. Say invoke three fundamental physical principles that are deeply entrenched in our macroscopic observation. What is that macroscopic observation? Mass is conserved. Then we can talk about the Newton's second law. The force is equal to mass into acceleration, right? That is momentum. Then third one is energy is conserved. So it can change from one form to another. In general, we talk this in terms of the equations, right? Three equations. So first one is mass conservation, second one is momentum conservation, and the third one is energy conservation. So if we know, right, if we know the nature first, then the second point, we go and describe the fluid model. So what is that fluid model? You know that the fluid is a squishy substance, and therefore it is more difficult to describe like a solid body. So it is necessary for a researcher to adapt a reasonable model, right? So if we adapt a reasonable model, then we can apply the fundamental principles mentioned in the one. What is the fundamental principle mentioned in the one? The conservation, right? Conservation of mass, momentum, and energy, right? So the third step, then apply the fundamental physical principles of mass, momentum, and energy to the model of item 2, the fluid models, right? In order to obtain the mathematical equation, right, which properly describes the physics of the flow, right? So we use these fundamental equations to analyze any particular aerodynamic problem. So that is the third step, right? Okay. Whether we consider all these, say for example, mass is conserved, momentum is conserved, energy is conserved. No, in certain cases where the temperature is not involved, then I understand the nature of the flow and I don't consider energy. I consider only mass and I consider only momentum. Then I need to select the fluid model and then I need to proceed and obtain the equation and solve the equation to understand the physical characteristics of the aerodynamic flow. Right? So, fluid models are necessary. Of course, we will discuss about the conservation of mass, momentum, and energy. In turn, you might have gone through that in the integral form, probably in the fluid mechanics before, but still we will look into that. So, now we will look into the fluid models, right? So, what is the suitable model of the fluid which can be considered for the particular problem, right? Say, first one is what is the suitable model? Second one, how do we visualize this substance, squishy substance, in order to apply the three fundamental physical principles to it? The answer is three different fluid models can be defined. One is finite control volume, then another one is infinitesimal fluid element, and the molecular flow. So these are the three fundamental fluid models which can describe any fluid, right? So we will discuss the fluid models one by one, right? Say, let us start with the finite control volume approach, right? So this is the control volume, right? This is the control volume V. Here the fixed control volume, fixed in space with the fluids moving through it. That means the volume will not move, right? What is that? If the volume does not move and the volume is stationary and the fluids moving inside the volume, what approach it is? What approach it is? Anyone can answer?
Eulerian.
Yeah, Eulerian approach.
Yeah, so that is Eulerian approach. What about here? The fluid volume, it is a volume floating, right, on the fluid, right? So fluid control volume moving with the fluid such that the same fluid particles are always in the same control volume. But here, the fluid particles will be moving through it. So every time the observer have only the volume but the different fluid particles, right? So okay, so this defines the control volume V, and we have a control surface S. Now in either case, the control volume is reasonably large and the finite region of the flow, right? So the fundamental physical principles are applied to the fluid inside the control volume and the fluid crossing the control surface, right? So inside the control volume and the fluids crossing the surface, right? The two things are necessary. So therefore, instead of looking at the whole fluid flow, we can represent the flow field with the control volume model. Do you remember in the home, there is when the mother cooks the rice, she takes a sample, right, in order to generalize the whole rice, whether it is boiled or not. Similar thing, right? The control volume model. So we limit our attention to just the fluid in the finite region of the volume itself. Now, this is a control volume approach. Now we will go to the finite element approach. So let us consider a fluid element, right? The fluid element is, it is like we say, it is infinitesimal. The infinitesimal fluid element means that the fluid element size is so small, it is infinitely small. So this infinitesimal fluid element also have two characteristics we consider, right? So let us consider the infinitesimal fluid volume is dV, and this is the Eulerian approach and this is a Lagragian approach, where here the infinitesimal fluid element fixed in space with the fluid moving through it. And in the other one, we have the infinitesimal fluid element moving along a streamline, right? With the velocity v equal to the local flow velocity at each point. So this is a fluid element approach, right? And once you have the fluid element approach, then you can make it for the full fluid. So the fluid element is infinitesimal in the same sense as the differential calculus. However, it is large enough to contain huge molecules, right? In the molecular level, it is huge. So it can be viewed as a continuous medium because the continuum is a basic concept we have in the aerodynamics, right? Then the fluid element may be fixed in space with the fluid moving through it. Alternatively, we can move along with the streamline, right? So again, the ultimate point we want to discuss is this. Instead of looking at the whole flow field at once, the fundamental physical principles are applied to just that fluid element itself, which can represent the whole flow field, right? Now, 3 points. One is control volume approach. Another one is infinitesimal fluid element approach. Then the third one is molecular approach. Here, we know in actuality, the motion of the fluid is a ramification of the mean motion of its atoms and molecules. But when we study fluid mechanics, do we think about that? Do we think about atoms, molecules in the fluids? Absolutely not, because we think about the macroscopic approach where we go and start with the pressure, velocity and other relationships, right? So here the third model of the flow can be a microscopic approach, right? Here we have a microscopic approach where the fundamental laws of the nature are applied directly to the atoms and the molecules, right? So we usually use the suitable statistical averaging, right? For example, in the case of the hypersonic flow, where the density of the flow, density of the air at a certain altitude is really small, right? The density is very less in such a way that when the airplane flies, the fluid molecules hit the airplane one by one. That is what we had a discussion. The mean free path between the two successive collisions is mentioned as lambda, and then we had a discussion on Nutson. The distance between the molecules is comparable with the distance of the length of the aircraft. So in that case, we need to think about the molecular approach, right? So which has many advantages in the long run. However, in this aerodynamics, that is the fundamental aerodynamics or the low speed aerodynamics, we will be discussing mostly on the first two approach, right? Say start with the control volume approach or the element approach, right? So that's all the discussion in this particular lecture, right? And if you have any question, you can ask me, right?